Hello, today I'll show how to configure a set of nodes that run with different responsibilities within a single cluster. Our example implements several engines: a LiveView data layer with redundant nodes for high availability, a LiveView services-only front end to provide a load-balanced single endpoint for clients, a LiveView backup node with log-based recovery for data preservation during times when none of the cluster's engines are running, and within the data layer, a stream-based data source that publishes to all data layer and backup nodes. A TIBCO streaming cluster is made up of multiple nodes. Each node in the cluster is constructed from the same application archive. A TIBCO streaming node may have within it multiple servers, each running in a separate engine. Each engine is its own Java virtual machine. What makes this work when using the same application archive for every node is that each node does not have to run all available engines. I have a script to start the cluster. The first 4 lines install each node so that its node services are running. Note that the main difference in each install command is the selection of a different NodeDeploy configuration. Additionally, for nodes that run the same services, the port values are parameterized. The next 4 lines start each node in sequence, waiting for the previous node to initialize before starting the next. This takes advantage of Linux tail and sed to pause node startup until the prior node has reported it has started. It starts the backup node first to ensure tables are loaded from the journals from the previous session. Then it starts the data layer nodes, which copy the table data from the backup node, and each other using peer-based recovery. Finally, it starts the service layer front end, which is running LiveView Web for clients to connect with. This cluster is functional as long as 2 nodes are running, a data layer and a services-only layer. Data flows and users can connect. This cluster becomes highly available and load-balanced with a second data layer node. If either data layer node fails, the other continues the active queries. The cluster is able to recover from a full cluster outage when the backup node is included, since it stores the live data to disk. If I were running these nodes on geographically separate systems across a private network, which I am not for this demonstration, this setup would be a highly resilient cluster. Let me make a quick note about the architecture. We recommend you use a bus between the data sources and the LiveView tables for distribution. First, take data in from the external sources, in this example a feed simulation, and process that data. Then send tuples ready to be written to the tables to the bus. All LiveView data layer servers read from that bus and populate their tables. The bus might be any fault-tolerant bus like TIBCO FTL, Kafka, JMS, and many others. Let's look at the configuration. Between projects, some configurations have the same file name. This is not a problem. What is important is that every name within the configuration is unique across all fragments that are included in the application archive. Configurations with the same name property value are considered different versions of the same configuration, and the last one to be loaded based on packaging order will replace the others. If multiple configuration files have the same name and version, this is a conflict that prevents installation of the node. The application's pom.xml dependencies determine the separate fragments that will be included. Fragments may in turn depend on other fragments. The application pom.xml dependencies only include the top-level fragments, which will become their own Java virtual machines, and does not directly depend on other fragments or include any transitive dependencies. With this pom.xml configuration, the application will have every kind of server included. It is the application definition and NodeDeploy configuration that will determine which types of services run in each node. The epadmin command line references each of these configurations as so, where the supplied node name matches substitution variable epNodeName, and the referenced NodeDeploy configuration identifies the node type, which identifies the fragments to run in that node. By specifying a NodeDeploy with a node type, the fragments to run are limited to only those allowed by that type. Let's see what engines are running. Each of the data layer peers runs 2 engines, as configured from the app.conf node types and selected by the NodeDeploy configuration used. So where's the data publisher in these engines? It is running as the second engine in each of the data layer nodes, which are also running the LiveView fragment. At this point, we understand how to configure an application archive with multiple fragments, and how to deploy that application into nodes that fulfill different roles within the cluster. In summary, to run multiple nodes in a cluster with nodes serving different roles, depend on all fragments, which are to become their own engines in the application pom.xml. In the app.conf, create node types that specify the fragments to run. Create a NodeDeploy configuration for each node type. Install each node using one of the NodeDeploy configuration files so that its type is determined. Thank you for watching. You may leave your comments here or visit our community site. And of course, don't forget to subscribe to this channel.